All right, welcome back. So we're having a look at areas because we've been doing areas, I know that, but there's just a little bit of a few ideas that I just want to fill in. So the first thing to consider is that when we find areas, we're finding them with regard to the area under the curve. So in this case, for example, if I nominate A, okay, some value x is A, and some value x is B, the area that we'll be finding when we integrate this function is the area under the curve. It's the area, it's that irregular geometry below the curve. Okay, it's all of this irregular geometry under the curve. Some of those values are going to be positive, and some of them is going to be negative, and some of them are going to be combinations of both. Sometimes they'll be positive and sometimes they'll be negative. So what does it mean when we get a negative result in our integration by area? In other words, what does minus some number units squared mean? Now, you've never been taught at school that there's such a thing as negative areas. So that's why we're addressing it. Because there aren't negative areas and we're not going to change that. Okay? We'll get positive square units, and that's just the way that it'll work. Okay? In the case of an area that's under the x-axis, for this case here, then what's going to happen is we will in fact get an area between the function and the x-axis, but the result will be that we will get a negative unit squared. So for this one here, we're going to get positive units, whatever the number is, units squared. For this one here, we will actually get negative units squared. That is a little confusing because it implies a negative area, but we don't say that. We don't use the phrase a negative area. But it's important because when we go and do a composite style function that results in and I'm using composite because it's composite interval, that is, we're going to be having moments of positivity added together with moments of, there's our positivity still, we'll let that one come up. So there's our positive, but look at this. We're going to have, let's call that D, I think. I'll make that clearer. Let's call that D. And for D, we're going to have B there. And this one here will be C. So we'll have splitting this up. Between A and B is positive. Between C and D is positive. But these guys are going to represent a negative area. Now all it means is that it's underneath the x-axis. The subinterval will have a negative A. This will have a positive A. This one here will have a negative A, whoops, and a positive A. And so when we add them together, so there's a composite idea, okay? When we add them together, we will get a total area that is the sum of each of the interval areas, but what if one of the interval areas is itself negative? Okay? So we'll end up getting this kind of thing. And in any combination, okay? So this would mean that we would integrate between A and B some function, and then we would also have a negative output from B to C for the same function. And then for the final bit, we would add C to D for that function. So exploring the possibilities of areas being added in this way is what this little bit is about. So sketching those is something that we want to come to terms with. So let's have a consideration of an example with that in view. Okay. All right. So let's think about this from the point of view of this example, which says to us, let's do x squared minus 9. Find the area bounded by this curve and the x-axis, and then it goes and says, then it specifies the interval. It doesn't just say find between the x-axis, it's specific. Now that's got a plus and a minus to it, because what does this graph look like? Well, x squared minus 4, let's consider that. We could run off and just do an interval. X squared minus 4 dx, and we could do it between 0 and 4. We could do that. We could just run off and solve this, okay? And we wouldn't be wrong in doing that. But what I want to do is consider the actual curve, okay? So we can do that because that's up and under, isn't it? X 3 over 3. No x there, so we conjure 1, so that's going to be 4 up and under again. And that's between 0 and 4. No chain rule here by FTC. So our scaffolding will be the placeholders and the placeholders, and we'll put a 4 in there. And then our scaffolding will include the placeholders again. Drudgery, I know. Minus 4, so placeholders, and we're going to put a 0 in there. Now this is a polynomial, so these are going to be gone, so I'll just not even bother with those. These, however, will have 4 in them. 4 4s are 16, 16 4s, 40, 64. 64 on 3, minus 16. So we want to multiply this by 3. 1, not to change it. So we'd have 64 on 3 minus 6 3s are 18, put down the 8, carry the 1. 3 1s are 3, 48 on 3. So that's 16 on 3 units squared. Now what does that mean? Okay, and this is the point. So we can do the calculation. Great. All right, we can do the calculation. So we've been able to do that, but there's something not quite sitting here. So let's have a look at this. This is y equals x squared shifted down to minus 4. So it goes like that. What did we just compute? And in actual fact, I'm going to expand this along a little bit and have this go up here like this. And we'll have a look at that. Because what did we just compute? We don't know. This is where it's a little interesting. Now, if we solve x squared minus 4 is equal to 0, we'll undo. We'll undo both sides. Once you do to one side, you do to the other. Plus or minus root 4, which is plus or minus 2. Aha. So our x-intercepts solve gives x-intercepts. Solve gives us minus 2 and plus 2. Now, if we'd done the integration there, we would have picked up this area. But we weren't told to do that. We were told to do the integration here between 0 and 4. So what that meant was that we had a sum of a negative. This represents the sum of a negative and a positive. So this one here could be viewed geometrically as the sum of a negative area, right, added to a positive area to give us our final result. Those two areas giving us our total area. Okay, our total area. So this graphic piecemeal thing is important for us to be aware of. Now, the other thing we can do, of course, is we can just do the integral of this part, 0 to 2, for our function. Okay, and then we can sum that with the integral of the second part, which was from 2 to 4. So we can do two sets. Let's see what that looks like, up and under. Seems a bit trivial doing the same thing again, doesn't it? But look at the difference. So this becomes 2 lots. Lots of drudgery now, isn't it? I'm going to put a 2 in there. And in this one, we're going to put a 0. So this one here's a polynomial. So zeros in here will mean that this one doesn't add anything, so we'll just cancel that out. So minus 0. And then we're going to plus another set of scaffolding with, I know, drudgery. And drudgery. This time we're putting 2 in here, 4 in here. We get 4, 4, 2, 2. So we'll need to work those out. And these had a 2 in them. So this is 8 on 3 plus 8. That's minus 0, so we won't even bother with that. This will give us 4 4s, 16 4s, 64. 64 on 3 plus 16 minus. Now we're going to have to expand twice. So 2 2s are 4 2s are 8. Minus 8 on 3 minus 4 2s are 8 minus 8. So that's the expansion. Now we'll notice that there's a couple of things we can just cancel. Plus an apple, minus an apple. Plus 8 apples, minus 8 apples. So the final result is 64 on 3 plus 16. So we better just go and check that out. And what did we get before? 3 over 3. So we get 64 over 8. And 48 over 8. And what did we do wrong? What did we do wrong? Well, we added them. Okay, we added them. So what we need to do is recognise that when we have negative areas, we've got to put a minus in. Okay, we've got to put a minus in. This one here was negative, but I didn't account for that in any way, shape or form. So this one had to be negative. Okay, and so we were putting a negative across all of those. So it raises an interesting question in terms of net sums. Obviously what that would have done was make that a negative, and so we would end up with the same 16 on 3 units squared. But this is important because when you're doing this piecemeal, you need to be aware of this. Okay, we don't have a negative area. There's no such thing as a negative area, but we do have a negative integral. Oh, we don't have a negative area, but we do have a negative integral. So this is a very important moment. Okay. All right. Let's have a look at another one and see if we can't understand that process. So be careful When you're doing your integrals, please be careful. All right, so we've got the next one. We're not given any points of intersection, limits of integration, so we've got to solve. So we go ahead and solve. That means assigning y to 0. Been doing that for years and years. Maybe we can just take x out as a common factor and ask, when is this true? This is true when x is 0. And it's also true when the bracket is 0, which requires x to be 2. So they're our limits. Okay, we're going to go between 0 and 2. So the integral of 0 to 2 of x squared minus 2x dx. So it'll be up and under x3 over 3 minus 2x squared over 2, they'll cancel, and that'll be between 0 and 2. So we'll have a look at this in a moment. So we want now to do our scaffolding for 0 and 2. Now we get a bit lazy at this point, don't we? Say, oh, it's a polynomial, so we're not going to bother with a 0 polynomial. Be careful. If it's trig, can't do this. To a len trig. Must check. Must check. Alright, so this one here, we had our scaffolding and the 2's cancelled. So it's just a square, so we drop that in. 2 2's are 4 2's are 8. So we get 8 on 3 minus 4. We want to make that the same family. So it's 8 minus 12 on 3. 8 minus 12 on 3 is minus 4, 3 units squared. What does that mean, 1 1/3 negative? Okay, what does that mean? It means the total area, the net area, is below the x-axis. So if we check this x squared minus 2x, now we could go through and do a curve sketch of x squared minus 2x. What would you do? X squared minus 2x. This is one of those simple ones. You take the coefficient of the middle term, halve it. That's going to end up being something. We square it. It's just 1. That's the square number. That goes together with those first two numbers, plus 1. Now you can't just add 1. You've got to subtract 1. So that's our shifter. This is a perfect square in x and minus 1. Check it. X squared. X times minus 1 times 2 is minus 2x. Tick. Minus 1 squared is plus 1. Good. Shifted down to 0. Shifted down to minus 1. So this is a perfect square at plus 1. Shifted down to minus 1. And it goes up through 2 and 0. And the 0 and the 2 inform us that were our limits of integration, that the whole thing was negative. And so that's what resulted in a negative area. It's not really a negative area. It's a negative integral, but it's an area beneath the x-axis. Okay, so it means an area beneath the x-axis, or a net sum that's beneath the x-axis in this case. Okay, so lots of ideas churning over there, and certainly some food for thought. All right, I'll leave that there, and I'll be back soon.